Hi friends and my dear students. In 12th Physics second volume, uh, 8th chapter, 8.63, gamma decay. We already studied about alpha decay and beta decay. So when we are talking about alpha decay and beta decay, we already studied alpha decay is nothing but if you consider any parental nucleus X Z A. Z is called atomic number, A is called atomic mass number. Then this is called parental atom. Then it will become Y, that is called daughter atom, and it may be the atomic mass number may be reduced or 2. Here atomic mass number is reduced 4. Atomic number is reduced to atomic mass number is reduced 4 because one alpha particle is nothing but 2He4. 2He4. This is called alpha particle emission. When we say beta decay, beta minus, and beta plus. Beta minus is nothing but electron emission. Beta minus is nothing but electron emission. If you say X, Z and A parallel atom, then the emission of one beta emission, that is called electron emission, then we have to add Z plus 1. That is, daughter atom's atomic number increased by one number and the remaining atomic mass number is same, plus one electron plus antineutrino. When we say positron emission, antiparticle of electron is called positron, that is Z X A. It is nothing but Z minus 1 Y, then mass number is remaining unchanged. Mass number is remaining unchanged, and it was said to be A. Here, instead of electron, we are considering positron, and here the neutrino. In these three steps are very important to understand clearly about the alpha emission and as well as beta emission. In the first emission of alpha, the emission of alpha nucleus is nothing but 2He4. That's why the decay may happen only because of emission of one alpha particle along with some other particle. This is called alpha particle. Now, when we talking about or when we are speaking about beta decay are happen in two ways. One is emission of electron and another is emission of positron. Both are considered to be as a beta decay. Beta decay. But whereas the emission of electron, emission of positron, both are same charges, same masses, but opposite to the charge. But along with the electron and positron, there may be emission of some amount of energy of antineutrino. While emission of electron, E minus 1, 0, there may be antineutrino. While emission of positron, there may be emission of neutrino. That we have already studied very well. Here, we have to consider either alpha particle or beta particle element or in the excited state or in the unstable state then the emission may be happened or decay may be happened. Now, when we consider about X, X is called parental atoms, and now we are considered Y. Y is called daughter atoms. The daughter atoms is not in the ground state but in the excited state. But in the excited state at 10 power minus 10 power 11 second. 10 power minus 11 second. 10 power minus 11 second. That is very smallest time it may be. Very smallest time it may be stable in the excited state. Again, it comes back to the ground state or lower energy level. It come back to the lower energy level. During this period, there may emission of or emission of beta emission or alpha emission. This is a process we already studied. Now, after happened of alpha and beta decay, the daughter atoms not in the ground state remaining on the excited state. Remaining on the excited state. That's a very important concept that you have to understand. Emission of alpha and beta is happened. Remaining the daughter atoms are not in the ground state or in the excited state itself, and the lifetime of excited state 10 power minus 11 second. After this duration of time, then again it will decay to the ground level, by emission of photon, or it may call as gamma decay, emission of photon or gamma decay. This is a very important to understand the gamma decay. How the gamma decay which have happened. The excited state daughter atom are transmit the energy to the while jump over to the ground state, then the gamma radiation or photons, energetic photons may be comes out from this process. That's called gamma decay. Now, when you consider the excited state and ground state, this is called ground state and this is called the excited state. Then excited state, there are more number of elements are available. If the number of elements are high, then the nucleus of the element is high. Here we don't know when here all we are talking about one nucleus. The process are happened alpha particle or beta particle decay, or these are all happen only because of one nucleus, not one atom. The decay may happen only because of the changes in the nucleus itself. Now, if you consider the element or nuclei in the excited state are in enormous, let us assume that n numbers. We can assure whether this first nucleus may happen to decay to the ground state, or second one, third one, fourth one, etc. up to n. We don't know. We can approximately by probability manner we can say that within the duration of time there may be some amount of decay may be happened, but we can't give any assurance for the decay. That's an important concept. If suppose let you assume that one atom or one whole atom are jumped over from the higher energy level to the lower energy level, then there may be emission of electron volt energy emission of in electron volt. In case, if you consider the nucleus itself, jump over from the excited state to the ground state, then there may be a million electron volt energy or transmitted. That is the main concept that you have to clear. When the whole atom are in the excited state and shift over to the ground state, only few amount of electron volt energy are transmitted by means of photon or gamma decay. In case if you consider only the nucleus of a single atom or shifted over to the higher energy level to the lower energy level, then there is a possibility of getting million of electron volt. That's a very important concept. Now, here within this atom, n atoms, we can't give any assurance for any which nuclei or which nucleus is going to be decay at the moment. We can't give any assurances. So by means of probability, we can say by long period of time, or for example 0 to t. When you say 0, then the number is called n naught. That is, there is no decay is possible, then the total amount of nucleus here n naught. When after some times decay happened or gamma decay happened or photon may be emitted in the time of at the moment of t, then the remaining atoms or nucleus are considered to be n. That's the thing that we have to understand. Now, next step, how can we derive an expression for gamma decay? This gamma decay are in two-way process. One is straight away jumped from. If suppose you consider this is ground state, and this is called an excited state. Now let us assume suppose for example, if you consider boron, an element which is considered to be 512. That is, atomic number is called 5 and 12 is atomic mass number. Now, this boron undergoes beta decay. If the boron undergoes beta decay, or you have to consider some other very good example. Let us assume the same thing. It is very easy. Boron atomic mass number is 5 and carbon atomic mass number. It will emit one electron plus gamma radiation or anti-neutrino we already wrote. Here this is called parental atoms. Here daughter atoms have to be carbon, and here atomic mass number remaining unchanged, but atomic number is increased to 1. This is a very good example because this atom in the excited state are straight away shifted to the ground state, then one emission of electron. You have to write like this or you have to write like this. Both are same. Here the amount of energy level difference between these two states is said to be minus 13.4 million electron volt. Now, this is a very important concept to understand. The boron is the element in the excited state, and beta decay which are happened. Beta decay means beta minus decay. Beta minus decay are happened, that is emission of electron, or straight away to the ground state. And that during that period there is 13.4 million electron volt. Are you clear? Okay. Now, or in some other manner it may be decayed. How? In between excited state and ground state, that is called, it between state called intermediate state. Intermediate state. If suppose this boron or transmitted electron and emission of 90 million electron volt and change into carbon 6C12 of isotopes. Here this is not in the ground state, this is remaining in the excited state. This star indicates that this element or the nucleus of carbon isotopes 6C12 in the excited state itself, not in the ground state. That is, the star means excited state. It indicates that this is not in the ground state, it is in the excited state. So, only the emission of, it emits the electron, and only the emission of electron along with the radiation 9.0 million electron volt. Okay, what happened next? Next, the carbon isotope 10 power minus 11 second, it may be stable in the intermediate state. Again come back to the ground state by emission of alpha or gamma or photon, gamma decay or photon at the value of 4.4 million electron volt. 4.4 million electron volt. This is the secondary emission, second process of decay which have happened in the excited state to the intermediate state. Then in the intermediate state, the element or carbon or daughter element are in the excited state, which are identified by means of the star itself. So that this again in the excited state, and it was remaining here only few seconds of 10 power minus 11 second, again come back to the ground state. During this period, there is a emission of photon, then we get stable carbon 6C12 in the ground state. Now, adding these two is equal to, now adding this 9 and 4.4, that is equal to 13.4 million electron volt. This is another way of exposure of gamma decay. This is the gamma decay. It's a very important concept to analyze. This in the ground state it is stable. In the excited state it is unstable. Unstable nucleus emits electron and not straight away come to the ground state. Then amount of energy radiated is called the 13.4 million electron volt. In other words, in second way, it emitted the carbon isotopes or excited state. Same carbon are jumped from the excited state to intermediate state. During that period, 9 million electron volt are emitted. After that, it may be stayed here very few seconds, 10 power minus 11 second. Then it come back to the ground state. This is called a stable carbon. This is not stable. Here star indicates that excited state. Excited state. This is the process to understand the gamma decay. Here, this is the process of gamma decay. I hope you understand the what is the process of gamma decay. Gamma decay is nothing but, for example, if you want to give an example for gamma decay, X, Z, A, and then this is called parental atoms. This is called lateral atoms. Again, Z, A. There is no change in the mass. There is no change in the atomic mass number and the atomic number, but there will be emission of gamma decay, that is called photon. That is called photon. This is the valuable equation to represent the gamma decay. I hope you understand clearly about the gamma decay without changing of atomic mass and without changing of the atomic number also. Atomic number remaining constant, atomic mass number remaining constant, but an element may be converted into dot element with the emission of gamma radiation or photon. This is called gamma decay. I hope you understand clearly. Thank you, my friends. Next topic we are going to explain what is the law of radioactive decay. What is the law of radioactive decay? Yes, thank you.